Hi, this video is all about the different types of sandstone that we're likely to come across in A-level geology exam papers. To begin though, perhaps it's important just to reconsider for a moment, what do we actually mean by a sandstone? And to do that, we need to look at the classification of clastic sediments. A sandstone is a type of clastic sediment. These are defined by two key features. Firstly, the grain size, and secondly, the composition of the sedimentary rock. If we look at the classification of grain size first, we use this Wentworth scale. You can see on the left-hand side of this table, we've got grain diameter shown in millimeters, and the equivalent then in microns. On the right-hand side of the grain diameter part of this table, you can see there's a measurement we just call phi. Now, phi is a simpler way of determining a more linear scale for grain size. We'll look at that in a different part of the course. For now, though, we can focus on the grain size in millimeters. Let's start by looking at the larger grain sizes. So if we look starting at 256 millimeters and coming down, we've got different types of perhaps what we could call gravel, going all the way down to 2 millimeters, which would be defined as a granule. If we look down at the bottom of the scale, at the mud type rocks, again, the grain size will define whether we're dealing with clay or silt. The maximum size of silt is about 1/16 of a millimetre, 0.0625 of a millimetre if you prefer it decimal. Therefore, everything in between, from 1/16 of a millimetre up to 2 millimetres, is going to be sand. Now, we could further subdivide these sands depending on their grain sizes, as you can see in this table. But for what we're going to talk about today, we don't need to worry about that a great deal. We differentiate, as well as by size, on the different types of sand, by the different compositions. And the compositions of sands can tell us a lot about the environment in which they were deposited. There are 4 sands really we need to know. I'm going to show you 4 photomicrographs, pictures taken down microscopes to show us the texture and composition of these sands. The first one here is an orthoquartzite. This is a sandstone which is almost entirely made up of quartz. The colours you can see here, or the tones really more accurately, all going all the way from white through different shades of grey through to black, are all indicative of quartz. This tends to be a very mature sediment. It's a sediment where all the other minerals have been weathered and eroded away and have only left the quartz behind. This is the type of rock we might find in a high energy beach environment, or perhaps in the lower courses of a river. You can see with this particular example, there's been some compaction of the sediment, and the grains have even just started to sort of fuse together a little bit. Not quite enough, I don't think, for metamorphism, but there's been a lot of compaction and cementation to make this rock as we see it. Now, if that's a very pure quartz-rich sandstone, the others that we need to look at are perhaps a little more diverse in their mineral makeup. The second of our sandstones is one we call arkose. Now, just by looking at this photomicrograph, comparing it with the previous one, we can see that Arcos has got a greater variety of minerals in there. We still have the quartz, like we saw in the other quartzite, but you can see some very distinctive feldspar there with the sort of striped appearance, and clearly some other minerals as well, possibly even a bit of mica in there. But it's that feldspar that's crucial. Arcos is a sedimentary or sandstone, sedimentary rock, that contains a significant proportion of feldspar. Often that feldspar will be quite weathered and quite battered, but it will be there. Now, as we know, feldspar weathers in water. This is the type of deposit we find from a desert river. A river perhaps that won't have water in it all the time, what we call an ephemeral stream. So the water will flow for brief periods of time after rain in the desert and then deposit this sediment behind it. So the feldspar doesn't have the prolonged exposure to water that would lead to the hydrolysis and breaking down of it into clay minerals. It tends to be quite an immature sediment. You can see as well it's quite poorly sorted, this example. For even more of a mix, we look at a greywacke. If we look at this particular example, you can see again it's poorly sorted. The clasts in this also are quite angular, indicating low levels of maturity, how this perhaps has been eroded and deposited relatively quickly. And there's also a great mixture of materials in here. Again, we get quartz. It's fairly common in all sandstones. But we also get a mixture of all sorts of other things. Maybe some feldspar. We can see some small examples of the sort of striped, distinctive grains of feldspar. But also what we call lithic fragments. Dark coloured, fine grained, sort of not terribly identifiable pieces of rock. Lithic fragments is a geologist's way of saying bits of rock we can't identify. This is quite a diverse mixture of materials, a dirty sandstone, if you like. It's common in deep sea environments, particularly what we call turbidite deposits. The final sandstone we need to look at is, despite the appearance here, a red sandstone. It might seem odd calling this particular example a red sandstone, but this rock has been sort of stuck together with an artificial resin. That's what you can see as the blue colour. So that blue colour would represent the porosity of this sediment. We know that red sandstone tends to be quite porous. You can see from this example, this sandstone is quite fine-grained and also really well sorted. There is rounding as well of these grains. It's hard to see on this. It's the very sort of thin, dark outline of many of these grains of sand, but that's the hematite. Hematite cements this sediment together, often poorly, but also gives it its colour. This thin section, though, reveals that hematite is only a tiny proportion of the overall composition of this rock. It's just a very thin coating on the grains. The bulk of this rock, as we can see, is quartz. A red sandstone is a typical desert deposit. The type of sand that gets blown around by the wind and forms into sand dunes. Okay then, to sum up, This is a triangular graph. It's the way geologists represent data where we have three different elements making up a rock. We can see from this that sandstones are a combination of these three different elements: quartz, feldspar, and lithic fragments. Now, quartz is such a common mineral in a sedimentary rock that we don't see very commonly at all sandstones that are made predominantly of feldspar and lithic fragments. Quartz always is a significant element in the composition of a sandstone. If we have a great deal of quartz in a sandstone, with less than 10% lithic fragments and feldspar combined, so it's a very pure quartz-rich sandstone, that makes for an orthoquartzite. If we have more than 10% lithic fragments, and often it's far greater than that, then we describe that sandstone as a greywacke. An arkose then will be richer in feldspar, more than 10%, often perhaps up to maybe 25% feldspar. Something to think about though. Where would you put a red sandstone on this diagram? Draw it in on your notes. Okay, to conclude, there are different types of sandstone classified by their grain size and their composition. And each of those types of sandstone is indicative of a different set of processes from a different environment. It's important to remember which one goes with which. Don't forget to come up with your interesting question and bring it to class. I'll see you then.